Alright, so what I want to do in this video is just show an interesting effect that I've noticed that has to do with uh, highly charging well, what this is here is a test tube with a powder inside of it. That powder is mostly cobalt oxide, and then wrapped around it is aluminum tape with electrical tape for insulation. On the inside here is a thin wire that goes down the center, and so what I'm going to do is charge this up to about 20,000 volts positive. So what that's going to do is electrify the cobalt oxide powder in there, and the field lines are going to go radially outward like that, more or less. Not exactly, but that's the idea. So what I think is happening here, well, let's just do a quick test. So this this dish here is an aluminum, it's a reflector dish, but I'm using it as a sort of a Faraday shield, just to shield the meter from any kinds of magnetic transients that might pass through or affect the scale. And what I have it, and I have it grounded here. As you can see, got it hooked up here. This goes to ground, to the mains ground here. And this is my power supply, neon sine transformer, and I have a couple of stages here, diode multiplier. And that just goes into here. So it's a pretty simple setup. So I'm going to fire this up, and I'm thinking, well, based on my experience, the scale here is going to dip negative. It dips negative when I charge it positively, and vice versa. So let's see what happens here. Okay, so this is my high-tech switch. I'm just going to plug it in here on the count of 3. 1, 2, 3. Okay, looks like nothing. Okay. Well, didn't feel like doing anything that time. So what I'll do is try disconnecting the ground. Just zero that out. Oh, I gotta discharge this because this gets quite a charge in there. And so the dielectric, it's a dielectric in there, it has to relax. So kind of takes a while for that to happen. Anyway, so let's just see what happens here. So this dish is not grounded. Here we go. 1, 2, 3. -3, -2. Okay. So that's what I've been seeing. But I've seen even bigger transients than that. I'll show you what I mean here. So if I take this off, what I did before is I had this steel plate on here to shield it from any transient magnetic fields due to the fast charging of this dielectric here. So that's basically it. See what happens here. So this is -1. Well, I was seeing it going down to like -26 before. Why it's not doing that now? I guess that has to do with the dielectric. I'm just going to let this settle for a minute. Okay, so let's try that again. 3, 2, 1. Nothing. And my multiplier's been flashing over a little bit. I don't have it properly insulated. Alright, I'm going to try this one more time with the aluminum dish here. And so it's not hooked up to ground or anything. So count of 3, 1, 2, 3, -5, -2, and then it should settle down to 0. There we go. Now I'm going to unplug it. 1, 2, 3. And it should go positive a little bit. I'm going to discharge it here to ground. There, see, it goes positive a little bit. And that's what I've been seeing a lot. Now I'm going to, again, hook up the dish to ground here. Ground it out. And 0 that. And see what happens. Maybe nothing. Yeah, nothing. And I'll discharge it. Goes positive. Okay. Okay, so now I've hooked it up to, this is a negative multiplier. This is going to do negative or minus 28,000 volts here. Okay, so let's see what happens. Ground is not connected. One, 2, 3. And that's what I thought. The multiplier is screwed. Alright, so now what I've done is hooked up a different voltage multiplier. This one will produce a negative output now. Should be negative 28 kilovolts. Ground is disconnected, so let's see what happens here. One, 2, 3. See how it goes positive. Now I'll turn it off. 1, 2, 3. Goes back to 0. Now I'll discharge it. It might show a negative. Well, negative dip. No, it didn't. Plug it in again. So 3, 2. It's a little bit of a thing there. Now I'm going to hook up the ground to the dish. -3. Okay, so I'm going to attach it here. And that's just from the lead. Let me just reset this to 0 and discharge the dielectric. Okay, ground lead is hooked up to the dish. Count of 3. So this is negative 28 kilovolts. 1, 2, 3, 0. Okay. One other thing I'm going to try. Okay, no dish, so it's just negative going into this powder here through the wire. 1, 2, 3, 0. I'm actually not getting much voltage out of this thing, so I don't know. Should be getting a longer arc. See, for 28 kilovolts should be longer. So now I'm going to unravel all this tape. I tried making a capacitor with this a while ago. It would be an asymmetric capacitor. And then, so I hooked this up to ground. When I powered it up, it just showed 0 on the scale. But when I had one wire wire attached to here floating, I would get a spike there. So I'm gonna take this tape off here. Before I do take all the aluminum tape off, I just want to see, I just got that hooked up there to ground. I just want to quickly check, see what happens here. 1, 2, 3. Nothing. Okay. Okay, so a little problem with these. Looks like I think this capacitor here in my multiplier is burning out or something. They're 20 kilovolt capacitors, so it should hold up. Maybe I need to add a resistor. Anyway, I'll figure that out. Alright, so I just want to try a few more things here since my voltage multipliers have failed for now. So I'm just going to try the Wimshurst machine again here. That's a gap there about, well, let me measure. That would be about 50 centimeters. So, yeah, it's probably, oh, I don't know how many thousands of volts that is. It's a lot. So, just keep an eye on the scale there. This is the same thing. This is the, see, this is the test tube without the aluminum tape on it. Okay. So whenever there's a spark discharge, it goes negative. And then I put it on the other electrode. Bet you it'll go positive. Yeah, it goes positive a bit. Now correct me if I'm wrong, but this is a steel plate here. As you can see, it's quite thick, so it should absorb any kind of magnetic transients that might come off of this before it hits the scale. give that a shot. But I'm seeing more fluctuation there. It goes negative as it charges, and then as it discharges, it goes positive. And now if I put it back on the other lead to change the polarity, now it goes positive, and then when it discharges, it goes negative. So it's the opposite. And the funny thing too is, with electrostatic attraction, you know, I used to think maybe it was being attracted to the table, but when it's fully charged up, so when it's like at equilibrium, when the charge accumulated in here should be the maximum, the attraction pretty much goes to zero. But when there's a transient, a discharge, see that massive fluctuation? See, that's the gap right there. That's even wider than before. I don't know, that's probably like 6 centimeters? I don't know. I find it pretty hard to get these voltages off a diode multiplier. Haven't got there yet. Oh. Now I like to try sometimes just random stuff. So I just have this big aluminum ring here. And that's the setup there, so it should go negative on charge up. Let's see what happens. That's the gap length there. Okay, so now what I've done is hooked up these plates here to the other side of the generator. So instead of just leaving it floating, I'm now going to ground it up to the opposite polarity. See what happens with that. That goes crazy. All right. Now I'll try reversing the polarity. Okay, polarity reversed. Looks like it's going. Oop. Scale can't handle it. Hang on. Okay, here we go. Positive. When it discharges, it goes negative. least it did the first time. So I just want anybody out there who's really smart with this stuff, like, tell me if you think there's any ion wind thing going on here. I don't think so, because this here is quite insulated in this plastic tube, except for this point down here might give off some ions. Maybe these edges, not sure, but the thing is the fluctuation during the transient, during the discharge. Okay, so what I got here is this is manganese carbonate. Manganese has a high nuclear spin, 5/2, and at 100% abundance for the main isotope. So that's why I'm looking at this, as well as the cobalt. It's very similar, 7/2, 100% abundance. And I think that's important for these kind of experiments. So just want to see what happens with this. Manganese is paramagnetic as well, so it's making a bit of a powder. That's crazy. Okay. So the theory as I understand it, is that the electric field, as it very quickly builds along or just outside of the wire in the test setup, in the test tube, it very quickly polarizes the atoms in the mixture of cobalt oxide. And what that means is it pulls the electrons towards, radially towards the wire, and stretches the atoms and pulls the electron orbitals, the electron clouds, over to one side of the nuclei, causing them to, which creates the electron orbitals have a magnetic moment, and when those orbitals are pulled over to one side, that orbital magnetic moment then acts on the nuclei, on the cobalt nuclei, which has a net magnetic moment, and causes those nuclei to shift, to align. And as that happens, it causes a fluctuation in mass, similar to the idea of compressing and expanding something like a gas. When you compress it, you constrain the motion of the atoms, you constrain the motion so that that kinetic energy is lost in the form of heat. So in the sense of this, I'm not going to say what kind of energy might be coming out of this substance when it's being suddenly electrified, only that it seems to have something to do with the mass. And then when it's relaxed, or when I shut the power off or discharge it, then it goes positive, or it goes the opposite. It spikes above zero or below zero, depending on the polarity. What we're seeing, or what we saw in the video, seems consistent with that theory, with that idea, although it is difficult to prove. Another difficulty is that I don't always get the same results, which is a bit puzzling. What I have observed is that when there are sharp points or wires that are in contact with the atmosphere and they're highly charged, then ion clouds form, and those ion clouds can create a force. So what I've seen is a steady state, like a steady force that acts on the whole assembly. So it looks like it's lost weight, or but that's just the ion clouds. But with these experiments, it has to do with the transition, the moment, the time rate of change of the potential of the system seems to be the key factor that's linked to the change on the scale. Consider also, think about how when I put that steel plate underneath that the test tube and was energizing it with those pulses from the Wimshurst machine, how the scale changed. I would have thought that the steel plate would absorb any magnetic waves or magnetic transients that would come as a result of rapidly charging and discharging that one wire capacitor. So that's what I would have thought, but we saw something to the contrary there. And so at this point I'm still reluctant to call it a gravitational transient or effect, because I have a very skeptical mind myself, and I'm still working through this, and with more experiments I hope to prove conclusively whether this is gravitational or not. And if it's not gravitational, could it be an effect of mass transients? As James Woodward in his writings and patents have, as he talks about there, with the rapid changing of or charging of capacitors as they undergo proper acceleration, which is real acceleration. And I thought about that. We are on this planet, and we are actually moving in circular motion, where the planet is rotating, and so we are actually experiencing centripetal acceleration all the time towards the center of the Earth. So with that acceleration, then if you're combining that with the charging of capacitors very abruptly, charging and discharging, we could expect to see mass transients happening there. So thanks for watching and sticking through this, and I hope you find this work helpful. And of course, if you like these kinds of things, what I'm doing and the direction I'm going, just hit subscribe, and because I'll be releasing more experiments along these lines. And until next time, cheers.